Okay, so this is the optics lab second experiment, lab number 3, because that's not confusing or anything. Thin spherical lenses. For this lab, what we're going to be doing is we're going to be measuring the focal length of various lenses by finding where it puts an image in focus on the near side and on the far side. The method that we're going to be using to do this is by, we have a diffuse light beam shining through this targeted reticule, which you can see is producing a target on our grid paper here. And between them we have the thin spherical lens. This one is a 48 millimeter radius of curvature. And what we're going to be doing is moving this distance so that it's out of focus and finding its two distances of focus. You have one on the near side, and then you also have one on the far side. Now, it's actually very difficult to see in the video, but here on the far side, on the video it looks like a dot, but we can clearly see the reticule now and tell that it's in focus. So our methodology is that we are going to be recording the distance that the target is at, and we are going to be recording the near distance of focus and the far distance of focus. And we're going to call this one D1, this one D2, and then we're going to be using some algebra to use that and the focal length, the distance between the screen image and the target object, which is the reticule. We're going to be calling that L. This is going to be D1, this is going to be D2, and then we're going to be using the equation, the focal length equals L squared minus D, which is D2 minus D1, divided by 4L. So L squared minus D squared over 4L equals our focal length. That is the equation we're going to be using. So without further ado, we're going to get to taking some measurements here. Now our target length is at, we're going to set it to 335 millimeters. The reason we're offsetting it a little bit is because we have to offset our target distance. That just makes the math a little easier.
That should be at 35 already.
Okay, yes, that's already at 35. Right.
Now, when I go to focus this, I'm looking more towards the center to focus it, just so I can get consistent numbers. So I'm looking at about right the middle here, that middle line, and the clearer the line is, the better I feel the focus is. So I feel that point is going to be a good point. The measurement I get is going to be 96 millimeters. That's our D1 position. Now moving over to the D2 position. This one's a lot smaller, a lot harder to tell when it's focused. So on this one, I just try and get the center to be as clear as possible. That's going to be about there. And that one's going to be at 280.
So the 35 millimeter offset would be a problem, except for the fact that we're taking a measurement of D1 to D2 and then subtracting the two, so the 35 millimeter offset does not actually matter for anything. Okay, so that is the measurements for the 48 millimeter lens. All right, so now that we're measuring the properties of the concave lens, the method that we're going to be using is a little bit more complicated. What we're doing is we've got it set up where we have the light source here, here we have our reticule containing object, and here we have our 22 millimeter concave lens. Now, the method that we're going to be using to find the properties of the lens requires finding what's called a virtual object, which is the object that appears to exist as you stare into the lens, because of the fact that the lens is not focusing downward, but rather opening up the light rays. What you need to do is look down into your lens and find the distance from the lens to where the virtual object is, and put an object that appears to be in the same distance there and measure what that distance is. So if I do that here, now for brevity of video, we're just going to be doing this measurement once. In the actual data that we took, we did the measurement 6 times because of the difficulty of getting an accurate reading, and then we averaged the results. So if, hold up the light, this one appears to be at a distance of 27 millimeters from the lens. So if I just write that down, and then place my screen, and now what we're going to be doing is using a lens with known properties. This is the 48 millimeter again, and finding its distances D1 and D2 based on a new L, not the L from the virtual or from the actual object to the screen, but rather the L from our virtual object to the screen. So for convenience, we're going to set up a good distance here. You can hold up the light. Yes. So that was at 135 minus 27, so it'll be 7. So I'm going to put this at 507 centimeters, so that we're a distance of 400, because this is at 135 here. Yes, so we're at a distance of 400 centimeters. So our L for this is 400 centimeters. And now we're going to record the D1 and D2. As before, I'm looking at the center to make sure it is focused. This one is a little bit harder to read. It's not centered. See if that helps. Nope. I'm going to go with right there. 174. That is our D1. Now moving over to D2. So this measurement is a lot harder because now I'm just looking at a little dot. So I just got to go with a point where the dot seems like it's forming an image. When the image is reduced to a dot, it's often easiest just to look at the point when the dot is the smallest, as when it's the most in focus. Unfortunately, there's a lot of sources of error in this this particular measurement. You have the non-objective nature of the subjective nature of figuring out where the distance is for your virtual image, and plus we have difficulties in measuring these distances. Did you get one?
Yes, I got 445.
All right.
No, 455, correction.
455. Okay. So that appears to be all of our data that we'll need to do our calculations.